Howdy class, this is chapter 2, lines and angles. We're going to learn a lot about equations here, how to create equations, how to manipulate equations, how to use equations, all linear equations. This first problem is about a cricket chirping. It turns out you can actually tell the temperature by how many times a cricket is chirping, and given by this formula right here, where y is the temperature in Celsius, and, in Fahrenheit, and x is the number of chirps. So think about it. What is the approximate temperature when a cricket chirps 41 times in 15 seconds? Now, x is the number of chirps in 15 seconds, recorded in 15 seconds. So in this case, 41 is x. So what we would do in this problem is we would substitute 41 for x and figure it out. Y, so y equals 41 plus 37, which is 78. So 78 degrees out in Fahrenheit when a cricket chirps 41 times in 15 seconds. Okay, suppose a cricket chirps 132 times in 1 minute. What would be the value of x? Well, x is the number of chirps in 15 seconds. So in 1 minute, that's 60 seconds. We would have to divide that by 4, or divide that by 15 to see how many groups of 15 seconds there are in a minute. And that would be 4. So to figure out the value of x, we would have to divide the number of chirps in 1 minute by 4. And that would equal 34 chirps per 15 seconds. Actually 33, sorry about that. Okay. And another way you could do it is if you know that there are 132 chirps in 1 minute, which is 60 seconds, then you want to know how many chirps there are in 15 seconds. And you could write a proportion like that and solve it that way. And you can see that we do 60 divided by 15, which is 4, and then we would divide 132 by 4 to get the number of chirps. All right. On a different night, Tony used cricket chirps to estimate the temperature to be 82 degrees Fahrenheit. How many cricket chirps did he count in 15 seconds? Tell how you know. Well, we know by this equation that the temperature, y, is equal to the number of chirps in 15 seconds, x, plus 37. So the temperature here is given as 82, so that we need to put in where the y is. And then we need to figure out what x is. And that'll be the number of chirps in 15 seconds. So 82 is equal to x plus 37. So we're trying to figure out what number plus 37 is equal to 82. One way we could do that, you learned last year, is by the balancing method. So if we subtracted 37 from both sides, subtracting 37 from this side leaves us with x. From subtracting 37 from 82 leaves us with 45. So he counted 45 chirps in 15 seconds if the temperature is 82 degrees. All right, just a little bit of information about past that we're going to be using in this chapter. This equation, y equals x plus 37, is a linear equation where the number multiplied by x is the coefficient or the slope of the graph, and 37 is the y-intercept. And if an equation is written like this, y equals x plus 37, it's hard to tell what's multiplied by x, but if you remember, multiplying 1 times a number is the same as the number. So we can think of the slope as 1. The independent variable is always x, and the dependent variable is y. If we want to write this in standard form looks like this. We learned this in the last chapter. We'll have some number times x plus some number times y equals some constant. So to put this in standard form, we would subtract x from both sides. So we get y minus x, or negative x plus y is equal to 37. All right. We're gonna learn these objectives in this chapter to determine from their slopes if two equations are parallel. That's what we're going to do in this lesson. Determine if 3 points are collinear. Collinear means they all line up in a straight line. To determine if an equation can be written in the form y equals mx plus b as a test for whether or not it's linear. To estimate solutions with graphs, here we are. To plot a set of data, identify outliers and draw a line of best fit, and to assess the limitations of a linear model based on the situation. So those are our objectives. Let's start by checking out some groups of equations and see if we can't discover something about them. In this group 1, right here, you'll notice that they all have plus 3 at the end. In other words, they all have the same constant term. In group 2, you will notice that they all have the same coefficient, negative 3 in every one. So let's graph those as sets and see what happens. So we're going to use our graphing calculator. And we are going to graph. I'm going to put this over here so I can see this. All right, we're going to enter these equations in there. Our calculator, so I'm going to press my y. And I'm going to put in group 1, and that's y equals x plus 3. All right, so I put all those equations in, and I'm going to press graph. And there they go. And we can see that they all, the slopes of all the lines are different. Some are increasing, some are decreasing. But one thing you should notice is that all of them cross the y-axis at the same spot. In other words, the y-intercept is the same in all of them. So in group 1, they all have the same y-intercept. And another equation that would belong in this group is, so we need the constant term in the equation to be 3. We don't really care what the slope is, so something like y equals 5x plus 3 would belong in that group. Okay. Now we're going to graph 4 equations in group 2. All right, I've graphed all those. I put all those in the calculator, and now I'm going to press graph. And we can see that every one of those equations is parallel. All of them are parallel. And the reason they're parallel, we can assume by looking at what they all have in common, is that they all have the same coefficient. The coefficient on every one of those is negative 3, and we know that the coefficient is the same as the slope. So in group 2, they all have the same slope. Another equation that would belong in that group is any equation with a coefficient of negative 3, like negative 3x plus 100. All right, in one group, the equations have different values for m, but the same value for b. If you start with a specific equation and change the value of m, how will the graph of the new equation be different? Well, if they all have the same value for b, b is the y-intercept, that means they're all going to cross at the same spot on the y-axis. So in the other group, the equations have different values for b, but the same value for m. If you start with a specific equation and change the value of b, how will the graph of the new equation be different? A different value of b gives it a different y-intercept. And a different value of m gives it a different slope. All right, so we're going to use that idea to try and figure out the graphs of lines that are parallel. So if we go back and think about the equations in group 2, we notice that they are all parallel. And that's because they all have the same coefficient, the same slope. If two equations in y equals mx plus b form, that slope-intercept form, have the same m value, what do you know about their graphs? We know they will be, they'll have the same slope. Explain why your observations make sense. And if they have the same slope, they will be parallel, as long as the y-intercepts are different. If they're the same y-intercept, then the one would land on top of the other equation or graph. All right, so let's try a couple problems here using this idea. Without graphing, decide which of these equations represent parallel lines. Explain. Well, one thing, to be parallel, we know they have to be linear, so we're going to cross out an equation that we know is not linear because it isn't in this form. To be a linear equation, we have to be able to write it in the slope-intercept form. And this equation right here is not in slope-intercept form, so let's cross that one out. Now, we think that A and C will represent parallel lines because they both have the same coefficient. And the coefficient is what determines the slope on the graph. So since they both have the coefficient of 2, we think they're going to be parallel. We can certainly check that on the graph if we're not totally convinced. So we can put 2x minus 7 and 2x plus 3 and graph them. And we should see that they're parallel, and they are. I'm going to stop the video here. I'm running out of space, but I'll continue the video on part 2.